So, hello and welcome to the third OpenGL workshop for beginners. And this morning we are going to talk about shaders. So we will have the basic introduction to shader programming. I guess that's one of the hardest topics to cover, to get into, but once you've got it, you really have the power to unleash all OpenGL capabilities. So for those of you who are new joining us today, let me just be so polite to introduce myself once more. My name is Niklas. I'm an OpenGL programmer and trainer for many years, and I'm from Germany, from the company deCode. We are a German-Romanian company covering all kinds of programming topics. And my passion and my business is OpenGL and general 3D programming. You could follow me on Twitter here. You see this on the screen now, or you should just stay updated about the OpenGL podcasts that I'm doing as well under OpenGL2go.net. So these are just the points where you should make sure that you follow us and check out about the news, because I will keep you updated there as well about new workshops upcoming. So yes, today it will be about shaders. So I need to give you a basic idea about what a shader is, and for this there is no other way than to come up with the OpenGL render pipeline. Let me show you this one. So the OpenGL render pipeline, actually this is what is happening on the graphic card when OpenGL is processing data for us. And it's very important to understand what is happening in what order. So I just will have a quick run through with you through this pipeline so you get an idea what is going on there. So this is the pipeline, as it is called, the steps taken one after the other to process the data. And in the beginning there is always this Vertex data, which means our geometric data that we provide for the entire OpenGL render process. And this data is just sent into the pipeline by our application. We did this in the last workshops, and we will do this today as well. And then a few steps are taken. The ones which are relevant for us today are the orange ones here, which is the so-called Vertex shader and a so-called Fragment shader. The Vertex shader is really processing every single 3D geometric point and is putting it to its final position. And while it's doing this, you may as well do some other calculations on this point or related to this point. You can all do this in the Vertex shader. This is what is happening there. Data that you have produced in the Vertex shader, modified, is passed further down the pipeline. The important point here may be the rasterization. In this point, the data is really rasterized, and from 3 corner points we get the entire 3D triangle. We really get the surface at this point of the pipeline. And after the rasterization step, we have a lot of so-called fragments, which are quite the same like a pixel. So think of fragments as a pixel first of all, just to simplify things. A pixel or fragment is not always a pixel, but let's just think about a fragment being a pixel for now. So every single pixel of a triangle that we draw is now processed in the Fragment shader. So if you have a triangle with, I don't know, 100,000 pixels, this Fragment shader gets called 100,000 times. This is something that you should keep in mind. And it's processing each of these pixels in parallel, individually. So all this processing is taking place at almost the same time. And after every single pixel has been processed, it's moved further down the pipeline here through the other steps that we will talk about in other workshops later as well. But for today, what we want to do, we want to manipulate the pipeline and bring in our own Vertex shader and bring in our own Fragment shader. And what you realize here as well, when we are working in the so-called programmable pipeline, this is what we do today when we use shaders. When we don't have a valid Vertex shader or a valid Fragment shader, there will be a hole in the process. And of course, it won't turn out anything. We won't see anything if we don't have a proper Vertex shader and a proper Fragment shader programmed and put into the pipeline and provided with the proper data. So this is what we need to do today. Once more, keep in mind, Vertex shader processing every geometric point. So for a triangle, the Vertex shader is called 3 times, of course, because the triangle is made up of 3 points. And based on the size of the triangle, we get maybe just 100, maybe 100,000 fragments, means pixels on the screen. So for each of these pixels, the Fragment shader will be called. So this is what we will try to do today. To do so, I prepared a file that we could start from today, because I don't want to code today from the ground up again. If you haven't watched the previous workshops, maybe this is the time for you to check the previous workshops and just check what we've done there. We will go through the example code that I provide now as well today, but it's if you're a beginner, it's really a good point to just watch the previous workshops on YouTube. You will find them easily if you search for OpenGL workshops there. The logo is quite the same like the ones that you can see here. But first of all, now in the Skype chat and in the Twitch chat, I will provide the link for downloading the data that we will start with today, what you already see here in my code block setup. And I assume that you have the proper setup for your code blocks like we had it from the last time. You could as well use, of course, your Visual Studio or whatever your IDE is, as long as you make sure your glue is working properly and your FreGLUT is working properly. There are different libraries that do the same. I will today use glue and FreGLUT for what we're doing today. So let me just post the link into the chats, give you a minute to download it, to put it into your favorite IDE, maybe modify even the header stuff. And then we can go through the code and first of all explain what it's doing right now. The code that I give you right now is actually not presenting anything on the screen. It's just our basic setup and we need to fill it with live. So let me just come up with the link in the chats. You can download it and I'll give you just a few minutes to set up everything properly. So, you should have downloaded the file by now and should have placed it in your favorite develop environment. And so we could just go through the code to give you a short explanation what is the basic setup of this one. So let me just increase my screen size here. First of all, we've got all our includes here because we are using FreGLUT and glue. So based on the compiler settings from the last workshop, you should know that we need this glue static to tell glue how to link properly. Of course, we need some regular C header files, C++ header files, and we need to include our glue and our FreGLUT to be able to work properly. I guess even in this example we would not really need the Windows H here, but I just included it. Anyway, so this is really just including stuff that we may need. Then I just came up with some global variables to keep it a bit more simple this time. Of course, in your final application you won't go like this, but this time we will just keep it like this. So I just came up with 3 integer values that first of all give us the width and the height of our window, how it should be created, and a variable to hold the handle to our window. This is something that you need to validate your window has been created properly. Then we've got some GL uints, which means GL unsigned ints. So these are the GL own data types, which usually are just the same like known C++ data types, but it's always good to use the GL own data types here. And I came up with a handle for our Vertex shader, for our Fragment shader, and for our so-called program. We will get to know this one later. First of all, just want to make sure these are just global variables that we will use in our code. And additionally, some other GL uints for the so-called locations in the shader, just something that you need as well later when we go on with this workshop. Then I came up with a solution. There are different ways to include the shaders in your application. You may just have them in a text file, in a plain text file, and load them while your program is starting. I just wanted to keep it all in one place, so I came up with a constant char array, which will be holding all our shader source. From the writing and reading, this may be a bit strange, but it just gives us the opportunity to have everything in one place and to easily check if we're doing everything right here. And of course, I did this once for the Vertex shader, and we've got the basic setup for the Fragment shader here as well. And if you know OpenGL already and you know shader programming, you may be a bit confused why I'm using such an, let's say, old version of the OpenGL shading language here. That's just because I want to make sure that we are using a version of the shaders that you may use as well in your browser WebGL application, as well in your OpenGL ES, so mobile embedded application for iPhone and Android, and as well on a desktop. Of course, on the desktop this may already be depreciated, but it's still working, so it's fine. What we are learning today is really a technique that you can use on any of your OpenGL application platforms. So if it is a browser, if it is a mobile device, if it is a desktop. So this is why we are starting out with quite an old version indeed. But again, these are just in the end char arrays, means strings of data to provide our shaders. So then we've got some forward declarations just to make sure the compiler knows what functions we are going to implement. We are going to have a resize function, a render function, idle function, and a create shader function. We'll just take a look at those as well pretty soon. Then, just like in the last workshop, we have a global array holding our vertex data. Once more, for those who haven't joined us last time, a vertex is just the OpenGL word, or in general the 3D computer graphics word for a point in space, a 3D or 2D geometric point in space. So this one here always just means X, Y, and Z for one point. So as I've got 3 lines of those, I've got 3 corner points, and 3 corner points perfectly make up a triangle. That's all we need. Okay, like any C++ program as well, this program is starting out with the main function. So here is where our program will start. And what we need to do, first of all, we will initialize the FreGLUT stuff. We will tell FreGLUT, in this case, what kind of OpenGL version we want to use. And this time I'm going for the major version 3, minor version 1, which means OpenGL 3.1 is our target version for today, because this is the lowest version that each of you should have that we could probably work with. So I'm pretty sure this is a version that all of you should be able to run on your machine. Okay, then we are just using, like I did explain it in the last tutorials as well, the GLUT init window size to just tell the window how big it should be. And then we are setting the so-called display modes for our window. Once more, if we tell him GLUT depths, that means we want to use the depths buffer, we want to use depths information in our scene. If we use GLUT double buffering, that means we have two pieces of memory which both somehow describe the size of our window, and we can write into one of these pieces of memory while the other one is being displayed, and when we're done drawing in the first one we just switch and show the other one. This just leads to, let's say, smoother visual output. And we tell our window we want to use RGB alpha color space. That's this last point here. Okay, after we've set this so-called display modes, we are ready to create our window, and I just give this window a name called shader. That's all. Then we need to tell FreGLUT as well some so-called callback functions. So what should happen in our application? So of course we need the reshape function. Once more, this is whenever our window size changes, OpenGL needs to know this, because OpenGL needs to know the relation between the width and the height. So there's a certain function that is called every time our window is resized. And keep in mind that the creation of a new window is also a resizing of the window. Then we've got the display function, which is just calling over and over again in a permanent infinite loop our own render function, and this is where all our rendering will happen. And we've got the idle function this time separately, which is a better way to do it than we did it last time. So we call our own idle function whenever the system's idle, so just think of it as some kind of background functionality. Okay, this is all for the FreGLUT initialization, and now we need to go with the glue initialization. And yeah, we just need to tell, first of all, glue init. So we just define a variable to store the result of the glue init, then we check if the result of the initialization is okay. Otherwise we need to quit our application because something is wrong with your glue installation. Then that's all we need to do for glue right now. Then we will call our own function called create shaders. In this one we will take care of the fact that the shaders are created properly, they are compiled, they are linked together, and the program will be created. This will be a major part of the workshop today. And as for now, we only need to set an OpenGL background color. We should just set our clear color to some value. As usual, you may put in here whatever background color you want to have. Just keep in mind that these are just the color channels, means the first one is the red, the second one is the green, the third one is the blue, and then we've got the alpha channel as well. And these values range from 0 to 1, which means 1 is full red, 0 is no red at all. Okay, after all the settings, we just tell FreGLUT to start the endless loop, to go into this permanent loop. So it's running and calling over and over again our idle function and our render function. So this is really our program is running. Okay, so let's go through the functions as well, very quick. Not as detailed as last time. Once more, if you don't understand what these functions are doing or what we're doing here in general, please go back to YouTube to one of the previous workshops, because we explained all the stuff in very detail there, and this should give you a good idea what's going on here. So, yes, the resize function. The resize function gets two parameters from the FreGLUT framework, and this is the width and the height of the new window. So how big is the window after it has been resized? We store these values into our global variables just to have access to them, and then we tell the OpenGL viewport how big it should be and how big it should make the area to draw in our window. As well, this one was explained last time in the workshop, so I won't go into too much detail here. Now just see, I did the clear color twice. That's of course bullshit. Let me kick it out here. You should do this as well. So it's not causing us any error. It's just bullshit that we have it twice here. Let's keep it once. In the resize function, that's okay. It's still not the best place to put it, but it's fine for us for this tutorial. Okay, what we've got here is our render function. So once more, that's the function which is called over and over again by the FreGLUT system to render our scene. So right now there's not much in it because this is what we will implement today. Just what I've got in here is to clear the background color and to clear the depth information, which means overdrawing everything which has been drawn to that point and resetting the depth information as well. And in the end, when we're done drawing, as we activated double buffering, we need to swap the buffers, which means which buffer should be displayed on the screen. Then we've got the idle function, which is doing nothing else but taking care of the fact that we are redrawing our scene. And we've got another function here which is called print log. I just brought in this one because this is the function for error checking that we really may need today when we're doing the shader stuff. So we won't go through it in too much detail, but indeed it's checking your shader or your program for errors and will display them in the command line. This will really help you to find your errors because debugging shaders is really a bit annoying, and without such a simple function here, it would take you way more time than it does anyway. So just accept that this function is there and that we will use it. Let's just fold it in. And we've got one more last function that we need to talk about, and that's the function create shaders, which we will use at the beginning, at the start of our application to create really all the shaders that we will use in our system. So I'm just checking here for errors once to make sure the error stack is empty. And then I'm checking if this function GL create shaders is existing and is available, because if it's not, then you are on a system where shaders are not supported at all, which is a bit unlikely because only very old machines should be like this. Or maybe the glue initialization has not worked properly. And this may also be a reason why shaders won't work. So this is a point where you may now already check when you compile this one that you see in the command line that you have shader support. And this is what we will do right now. Let me compile this one, although it is not producing any reasonable output. And after it's compiled, you may get a warning. You could ignore this one. I will run it. So there are two things that you should get from this one when you're running it. In my case, it's just a green window, but more important, I have also the command line output, which tells me shader support is okay. So my system is fine to run shaders. And this is what you should get on your side as well. And I just leave you alone for a second to check your compilation settings and your system if you really get this output, because this is what we need to start today anyway. Okay, hopefully you all got the setting now like this. So you've got just the green window and you've got the information that the shader support is fine. Once more, if not, you may just check your system which OpenGL version it really supports. You could just download the OpenGL extension viewer. Once more, the OpenGL extension viewer. Just Google this one. It's a free tool that you can download and install and run. And it will tell you what OpenGL version is supported on your system. And you should have at least 3.0, 3.1, so we can work properly. If you don't have it, just go ahead and update your graphic cards driver from your graphic cards vendor's homepage, and then you should really have this one. I guess there is no graphic cards vendor out there who won't provide this one, unless you really have a special graphic card. Okay, yes, let's just go and start the real coding then. Let me just quit this one here, and let's get back into the code. So we need to start programming our shaders, because everything that we do is based around these shaders. So there's the basic understanding of the shaders that we need. Let me just fold in all these functions here, because what we want to work on right now is this one here. We want to work in the Vertex and the Fragment shader first of all. So let me come up with the code for it. Well, first of all, these shaders are written in their own language, the so-called OpenGL shading language, GLSL. And this language is quite similar to C, so you won't have big trouble understanding how it's working. It has some of its own data types that we will get to know piece by piece. But first of all, it's its own language, and we just come up with some coding there. The major point that you should know is, of course, every shader again is a program in itself somehow. So we have a starting point, which of course is again a main function. So we just have a main function in any shader, which is the entry point of whatever we are doing there. And if we're opening the main function, we should close it as well. So this is just what is happening there. For the Vertex shader. The Vertex shader is processing geometric data, every single point on its own. So in the end, it needs to put out something, and it just indeed needs to put out one thing, and this is the geometric point. Because if the Vertex shader would not provide an output, then there is no geometric data, and without any geometric data, I guess we won't see much on the screen. So whatever you do in the Vertex shader, in the end, you need to have something there that says GL position is equals something. This GL position is a given variable that you just need to populate with a value with a vector of 4 to make sure that data is going down the render pipeline and that we will get some visual results at all. So this is the first major point in a shader, in a Vertex shader. You need to provide a GL position in the end. Just think of it as somehow a return value of the shader, which is not perfectly correct, but if you want to think in function terms, you could think of it as a return value. Okay, so we definitely need to populate this variable, that's for sure. But how do we get data into the shader? Where should this data come from that we populate it with? Well, this is the other point. We need to bring in variables into the shader which get data from our application. And whenever it comes to geometric points, all the data related to one geometric point is called attribute. So these are the so-called attributes, which means before we start our main function, we need to come up with a variable to get the data from our application. So let's just make one variable where we get our Vertex data into the shader. So as I just told you, all these are called attributes. So the variable type to be used in shaders is called attribute as well, which means you just write here attribute, which means this is an incoming variable holding data related to a 3D point. And then we need to tell them it's a vector of 3, which means it's holding x, y, and z. This vector of 3 is a data type existing in the GLSR language. And then we could just give it a name like with any other variables. So let's say it's our in Vertex, for example. Nope, just a semicolon. So this is really an input variable called an attribute type. Vector of 3 means it's just consisting of 3 values, x, y, and z. And that's our name, how we want to call it inside our program, in our shader. So in the end, this is what is coming into the shader. And as we want to put it out into the pipeline right away, we could just go ahead, copy and paste it down here. So what we've created right now is indeed a so-called pass-through shader, because it's doing nothing to our data. It's just receiving our data, and in the end it's outputting it to this given variable GL position, so we take care the data is processed further down the pipeline. So we've just created a pass-through Vertex shader, a very simple version indeed. Okay, this should be all we need now for the Vertex shader to get a visual result in the end. So let's just leave it like this and we go on to the Fragment shader. But first of all, make sure you've got your code like this. I just give you a few seconds to make sure you've got it really exactly spelled like I did here, so we don't get any problems later. Okay, hopefully your code is looking like this, so we may go on with the Fragment shader. The Fragment shader, again, just like the GL position in the Vertex shader, needs to output geometry. The Fragment shader, which is processed for anything a pixel on the screen, needs to output in the end a color value, an RGB alpha color value. And this is the only thing it needs to have. So as it is just a shader as well, it also has a main function. And we just need to make sure that we output in the end a color value. And this color value is also a given variable we need to populate. And this is called GL frag color. And this one receives a vector of 4, meaning RGB and alpha value. So we go with the OpenGL shading language variable type called vec4 and just tell them 0.1, 0.0, 0.0, and 1.0, which means we are outputting only red pixels. So whatever we are doing right now with these shaders, everything will be red, because we tell them whatever pixel you are working on right now, just make it red. That's all we do with this one. So just scrolling a bit here. Now we've got our basic, very basic shaders, but this is really all we need. Let me just move this a bit closer together so we can see anything on one screen. So the Vertex shader will process incoming geometry, and this is in the variable in Vertex. This is what we still need to do. We still need to bring in the data into the shader. We're just prepared the shader in that way that it's able to accept our input data. And we told him, whatever input data you get, you just take it and you pass it through further down the pipeline, so it will be processed by this given variable GL position. And then it's going through the pipeline. In the rasterization we get a lot of fragments. Once more, just remember fragments as pixels. And for every single pixel on the screen resulting from this geometry, which will be most likely a triangle, our fragment shader is called. And in this case, we are just going ahead and telling every single pixel, hey, you just get a full red color, nothing else. That's really simple, and you may also consider this a bit useless right now, but it's just a simple version of a shader pair that we can do. And we just want to keep it simple right now to understand how this is working. And then later we can extend the shaders anyway. So this is first of all the basic setup for a Vertex shader and a Fragment shader. So these shaders are just char arrays, mean strings right now. They don't do anything. So what we need to do right now, we need to take those char arrays and really compile them by OpenGL functions and really send them down to the graphic card to be used on the graphic card, and then get the information how to send the data to those shaders. But once more, at this point, just a few second break for you to check if your shaders look like this before we start to really going to use them. Okay, let's go ahead and really use these shaders. So where do we need to start? Of course, we have a function called create shaders in our application, and that's the best way to start with this shaders. So we go to this function, and after these lines which really check if the shader support is available, yes or no, we may start to use the shaders actually. So first of all, we need to create OpenGL shader objects. And at the very top of our script, I created already some variables to store information. So let me just go ahead, copy those, scroll down to the function we want to use them in, and just paste them here. And we make use of those now. So our Vertex shader ID. So we need to have an OpenGL shader object, as it is called. And that sounds a bit tricky, but it's very simple. It's just one function call, and this OpenGL function call is just gl create shader. And now we need to tell OpenGL what kind of shader do we want to create. Do we want to create a Vertex shader, or do we want to create a Fragment shader? So there are given built-in variables for this one. I'm typing like hell again today. So this is what it should be, GL Vertex shader, which is telling this function GL create shader that it should create a Vertex shader for us and store the handle of it inside our own variable Vertex shader ID. This is all we need to do here. So this just creates the shader first of all. Now how do we get our shader source, our char array holding the Vertex shader, somehow into this? And there's just another function for this in GL, which is called GL shader source. And this one again gets a few parameters. First of all, it gets the ID of our shader, so it knows what shader it should attach the stuff to. Then it needs to know how many we've got here. Then it needs to know the variable where our shader source is located. So in our case, this one was called Vertex shader constant char. There it is, yes. And in the end, we've got a null. I can't recall this parameter right now, but it does not have any meaning for us right now. So with this function, we tell OpenGL, you find the source for the shader in this variable. Once more, let me prove to you, that's just this one here. So it's just this char array means just a string. And it's taking this now as the source for the shader, which we can find by this ID, and this ID just means the shader we've just created. So this is really just giving the shader the source. So now we've got the shader created. Now the shader knows its source. What does it need to do? It needs to compile the source to check if it's really a valid one, if we have really written stuff which is usable. So for this one, we have got another function in OpenGL, which is called compile shader. And this one only needs to get once more the shader ID, as we already put the source for the shader ID, so it only needs to know the shader ID to compile. So these are indeed the three steps that you need to take if you want to create and compile a shader. You need to generate it, create GL create shader, tell them what it is, Vertex shader, Fragment shader. Later on at least on the desktop version of OpenGL, there are also other shaders that we may cover later in other workshops. Then you need to tell them my shader source is to be found here, please use it for this shader. And then we tell them, okay, now you've got the source, you know what you are, a Vertex or Fragment shader, go ahead, compile it. That's pretty fine so far. Of course, now it's a point where we need to check for errors, because otherwise we have no clue that something is wrong with our shaders. And for this, you may remember I brought in this function called print_log. So let's use it. Print_log. And the only thing it needs the shader ID. So 4 magic lines of code to create a shader, to give him a source, to compile it, to check if it has worked. That's not really spectacular so far. But that's it. That's why I simplified the code so much, to give you really the clear view onto how simple it is indeed. Now we've done this for the Vertex shader. And the nice part is for the Fragment shader, remember the shader which processes every pixel, it's just the same. So let me just once more move the lines closer together, copy them all, and maybe just come up with some comment. This is our Vertex shader. And this one here will be our Fragment shader. And now we just need to replace some variables. Of course, I already made a global variable to store our Fragment shader ID, so I replace it here. I use the function GL create shader, of course, but this time I'm telling him not to create a Vertex shader, but to create a GL Fragment shader, of course. So I'm just changing the type. Then we need to go ahead and tell him where to find his source. Again, it's now the Fragment shader, which should find his source. Now we can just make it like this again. This is our source for the Fragment shader, the variable we stored it in. So we just place it here. Just bring more to the visual section of the screen. So we just place the source here, tell him to use it for the Fragment shader we just created. And of course, when we tell him to compile him, we tell him again to compile our Fragment shader. And after this one, we check for errors on the Fragment shader. So you see, this is really just all the same. We just changed the variable to store the information in. We changed, of course, the source. And we changed the parameter for the create shader function to make sure we're really creating Fragment shader. So this one here has been used, I can delete it, and the rest is already fine. And before we go on, just check these lines and make sure they look the same on your side. Okay, hopefully these lines look just like the same on your side than they do on my side. So now we took our shader sources, the strings, we compiled them to something, and we have now two compiled versions of our shaders. Now the point is, first of all, shaders could never appear on their own. If you just remember the pipeline, shaders always need to be a pair. We always need to have a vertex and a Fragment shader working together. Only one of them, this won't work. So we need to somehow group them up into something, and this is called a so-called program object in OpenGL. So this is nothing which really is doing something. It's just a container to hold both of our shaders together in one place. And this is what we need to do right now. We need to create the so-called program object. We need to put into this program object our two shaders. And after we've done this, we can really use this. And this means we can really use our own shaders to render data through it. So again, these functions are quite simple. We always created here our program ID as a global variable. And let me come up with a comment here as well. program object. Let's create the program object. And of course, this one is as easy as the other stuff as well. It's GL create program. And this one does not need parameters because there's only one program type so far. So this is really just the container for the two shaders. So what we need to do now, we need to take our shaders and attach them to this program object. And for this, we've got another function which is called GL attach shader. And we need to tell him now to what program do you want to attach what shader. So to this just created program, we want to attach our Vertex shader. And of course, again, we do this twice. So I just double the line and tell him, okay, you've attached already the Vertex shader to the program. Now go ahead and attach the Fragment shader to this one as well. So we created a program. We attached the two already compiled shaders to the program, which is given by this ID. And now we need to tell the program, okay, now you know the both shaders, go ahead and link them, because this is necessary for them to cooperate, let's say. So there's another function called GL link program. And this one, of course, gets again the program ID. Just again, another magic 4 steps that we did, just like we did it before. Create the program, attach the Vertex shader, attach the Fragment shader, link the program, and you're ready. And you've got a program object for OpenGL, which allows you to be used inside your OpenGL render pipeline. And as we want to make sure that we check for errors all the time, we should come up with some error checking here as well. I'm not quite sure, is my print log function also capable of managing program objects? It should be. So let's just give it a try. So we tell him, check this program object for errors, please. So this is what you need to create the so-called shader program. Just remember, this is just a container holding the two single shaders in one place, so we can use it properly. At this point, maybe a good point to compile the program and to see if we get any errors so far. Although, of course, it won't work. Now we won't see anything, but it's just a good point to check for errors so we don't pile up too many errors in the end while we're going on coding. So let me just compile this one. The compilation looks fine. And let me run it. Okay, and here is why we are doing the error checking for. I get a nice error, and this is how the errors look, so it's good that it happens so you see it. So in my Vertex shader, I've got a problem. It says it cannot convert a 3-component vector to a 4-component vector. And that's perfectly fine. So let's check this line. But this is what errors look like on your side. And as you have coded it like I did, the error should be the same on your side as well. So let's just check it. So we need to go to the shader source code now. And we give in a vector of 3. But I put it into this variable GL position, which is a vector of 4. And of course, this needs to cause trouble. So I'm trying to put something into something else which is just not big enough. There are different ways to solve this. One could be, I could cast my vector of 3 to fit into the vector of 4. So let's do this. Vector of 4 consists of my 3 elements from my vector of 3. Plus an additional 1, and this makes up a vector of 4 now. So I'm really casting this vector of 3 up to a vector of 4 by adding one value to the end of it. And GL position is also a vector of 4, so I'm able now to store the data in it. So this change is something you should do as well on your side. And let me just check in the meantime on my side if I have eliminated all the errors now. Yes. And after I'm running it right now, I don't get any more errors, which means our shaders have compiled properly. And so the Vertex shader is compiled properly, we check this first. Then the Vertex Fragment shader is compiled properly, we check this in second position. And then the program has linked both of those properly to a program object. And we don't have any errors here, which means we are fine. So this is what we wanted to achieve so far. So make sure your shader looks like this. And make sure that your compilation of the shaders and the linking with the program looks like this as well. We've just done 1 hour now in our workshop, so it's time for a short break for each of us. Just a few minutes to grab something to drink, to grab some fresh air, and then we'll go on and start to use our shaders. So let's go on. Once more, we've got our shader sources properly, we've got our shaders individually compiled properly, and we've got linked them to a program. That's fine so far, but we need more. Because right now we've got our shader properly compiled and we can use it. But how do we get the data into our shader? Well, first of all, we need one more line to finalize this shader topic to make sure our shader is really in use. So we come up with a line GL use shader. I'm not quite sure why it's giving me the extension variation of this. So it should be like this, GL use program, which means we now want to use this program that we have created, which is holding our two shaders, and use this one really for rendering. So this is now activating our own shader program. Without this line, everything else is fine as well, but we are not using it for rendering. So this one makes sure I have written a program myself holding two shaders. I want to use this one for rendering. This one really puts into the pipeline, the render pipeline, our own shaders. So we need to make sure we use the program at all. We could do this as well shortly before we start the rendering process, but let's just do it here as our program is simple enough so we can do it here. So what else do we need to do? We need to know how do we get the data into the shader, and for this we need to know where our own variable is written inside the shader. So in the shader we have our variable called in Vertex. This is a variable name that we came up with, it's our own. So let's copy this one because we want to get the information how we can access this one, how we can send data to it. And this is what we need to do once our shader has been compiled. We need to get the location, the so-called location of this variable inside the shader. And there are given functions for this. And I also created global variables for this. Once more, let me prove this one to you as well. I came up with these variables called vertex location and color location, both with a prefix. This just means it's a shader location variable. I just did this for myself to make the code more readable. Right now we are only working with the vertex, no color till now, so we only need this variable here. So let's populate it. Okay, the S vertex location variable should hold the location of the variable with this name in the shader. And there's a function for this. And this time, as we are trying to get the location of an attribute variable, because I told you this vertex in Vertex is called a so-called attribute, there is GL get attribute location, and it has two parameters. First of all, the program it should look into, because in the program there's the shader included, so it knows it needs to check this program to find our variable name, and this is really the name, this is really the string. So we are telling him, please check this program for a variable with this name, and if you find it, give me back the location of it. And these locations really are always iterating figures, so it will start 1, 2, 3, 4, 5 and so on. So most likely we will get location number 1 for this variable right now. So this really just gets us the a handle where we can send data to into the shader, so our data from our program will really reach the shader. This is something that we need to do. Okay, so we just do this once. We just now know the location of our own defined variable inside the shader, and of course now we need to use it to send data there. So this all was just our setup, making sure our shaders are compiled, our program is running, and we know where to send data to. That's all we needed to do in the create shader function so far. So just make sure once more that you've got this line here as well, because this is what we need to do the next step to send the data there. Okay, now let's use this information. Let's use the information that we know where we need to send the data to the shader. So we close the create shader function and we go to our render function, because this is now where we want to work. So what we need to do again, like we did it in the other workshops as well, we need to enable first of all the input into the pipeline. And in our case, we know what variable we want to enable because we just got the location of the variable. That's some of the handle to it. So there's a function called enable vertex attrib. Enable vertex attrib array. There it is. And this one just gets this variable. So it somehow tells OpenGL, hey, I have a variable of my own in my shader, and I want to enable it for sending data to it. So we're really just opening a door here. We're just opening a door for the data to be sent to this variable. And as usual, whenever we enable something and we want to write clean code, we go with disable vertex I'm lazy now. Vertex attrib array, which means we just close the door again to make sure we have cleaned up our own code somehow. So we enable the variable here to be filled with data, populated with data, and we close it later after we've done our drawing. And in between this, our drawing should happen. So we need to tell OpenGL now, how do you read the data from our vertex array? We did this before with quite similar functions, and I told you that we can structure this array in any way that we want to, but we need to tell OpenGL how this array should be read. So we've got again data here in the normalized OpenGL space, meaning from -1 to +1, just to make sure that we see it. Just remember once more, when you don't use any metrics to describe your world, to describe a perspective, a camera view, or anything else, this default OpenGL world always reaches from -1 to +1, -1 to +1, -1 to +1. So we should stay in this range to make sure that whatever we do right now in our very simplified version here will be visible. So this is why I came up with these figures. Okay, it's just an array holding 9 floats, and it's accessible for us by this name. So I'm gonna copy this name first of all here, so I don't need to scroll so much up and down. And we need to tell OpenGL now, hey, I've enabled the access to this variable, I want to send data there, and how does the data need to be sent there? And there's a function for this, vertex attrib pointer, which will get all this information now. Hopefully my resolution is big enough to bring it all in one line, but I'll try. Okay, first of all, it needs to know where should I send the data, and this is really the location. We want to send the data, whatever it is, however it is structured, to this location, to our own variable inside the shader. So we tell him first parameter, this is where you will send the data. And now we tell him again, like we did it before, what kind of data do you get? How is it structured? Let me see if I can bring this onto one screen. I guess I can't. Okay, but anyway, we know our data consists of 3 floats which belong together, 3 floats which make up one corner point. These are GL floats, so we tell them. I need to small on the size here. Okay, we tell them here is where you should send the data. You get 3 floats that belong together, which form a one geometric point. You should not normalize the data. That's the next parameter. That's just GL false because we don't want to normalize it. There is no offset. You don't need to jump over any other information which is located in this array. It's all one after the other. And in the end we tell them here is where you find the data. So that's again quite a long line, but let's go through it once more. So we tell OpenGL, please send all the data from this array to this location in the shader, to my own variable inside the shader. And we tell them you always get 3 floats that belong together, so always send 3 floats together at one. And you don't need to normalize them, and you don't need to jump over any additional data. So this is really just explaining OpenGL how to read the data from our vertex array. Let me scroll up a bit. From our vertex array and send it to our own variable in the shader, which is hiding behind this variable here, which means sending the data here. So in the end, each point from the array will be passed to this variable one by one. So x, y, z, first shader call, x, y, z, second shader call. So for our triangle, which is formed by these 3 points, these 3 points will be sent to the shader once, these 3 points to the shader, and the next one. Means our vertex shader will get called 3 times and will always send the data here. And we're just taking this data, adding another force value to it because we need to have a vector of 4, and we just pass it down the pipeline. This is just what we told OpenGL by this line. We just told him how to read our data, and in the same function call we told him where to send the data. So this is where to find the data, how to read it, where to send it. Again, this is just configuration. Nothing has been drawn or sent till now because we just told OpenGL how to read it. If we want OpenGL to draw this now, we need to come up with the function which actually tells OpenGL, now you know how to read my data, where to send it, go ahead, please draw it. And again, this one is GL draw arrays, like we did it in the other workshops as well. And we need to tell OpenGL what we want to draw again. Now we're again at this primitive type, which means do we want to draw points, lines, triangles, whatever. We want to draw triangles. And we want to draw from the very start of the triangles 3 points. Means starting at the beginning of our vertex array and drawing the first 3 points. And how does he know what a point is? Well, we told him 3 floats together make up 1 point. So 3 times means draw all the 3 points. So this is the basic setting that you need. Enable this location in the shader, which means our own defined variable in the shader, to be written to. Tell him, okay, write to this variable, get the data from here. This is how the data is formatted, and you don't need to jump over any data. And once OpenGL knows this, we can tell him, okay, now you know everything, how to draw it. Go ahead, draw triangles, and take the first point and then the next 3 to draw this triangle. And in the end, we are just cleaning up again, nothing else that we do here. This should get us a first proper triangle rendered onto the screen. And if you want to know what would be the color of this triangle, hey, we defined this because in the Fragment shader, which is automatically used now as well, we said that every pixel will become a red pixel. Remember, this is R, G, B, and alpha value. So we will get a totally red triangle if we have done everything right here, which I kind of doubt because I always bring in nasty bugs. But let me check this one. Our first time in this workshop series, something works on the first strike. Okay, this is what you should get. Again, that's not very spectacular, but what we have now, we have a triangle rendered through shaders. We are using the most modern technique for 3D rendering. We are using shaders. Of course, the difference is not that big. It's just like the rendering that we did in the last workshops using the fixed function pipeline for OpenGL. Right now, we are using the programmable pipeline. And once more, this technique is used for any mobile device, iPhone, Android, whatever. It could be used on any modern desktop device. It could be used in the browser nowadays with WebGL as well. So this is really the major way to do programming today with OpenGL. There are, of course, a few more points in very modern OpenGL shader programming that we will come to later as well. But first of all, if you have the red triangle right now, congratulations, because you really made a major step into the right direction. Just take a few seconds to check your code is looking like this and your result is looking like this before we go on and play around with this shaders to get a better idea of what is happening here. Okay, so hopefully this is working on your side. If not, just as usual, while the workshop is running or after, we may just chat in the Skype chat to see if we can fix the problem on your side as well. But now let's just try to extend this. Right now we've just got a red triangle. We brought in the geometry probably. Let's bring in colors now as well, just to give you an idea how to get additional information into the shader. So, we've got two ways to do this. We could just add the color information here in our vertex array. First of all, let's keep it simple. I don't want to confuse you more as necessary. So let's copy this one and come up with an additional array called colors. And let's just give the 3 corner points the RGB values. So we go here with 1.0 and the rest. First of all, I just go ahead and make them all 0, that's easier. And then I just bring in RGB values. for this one. Set up the array for the colors. So we've got a color array just like the vertex array. Remember, those need to be structured somehow the same so that these geometric information correspond with this color information. That's the first step we need to take. Shouldn't be too hard for you to copy this one and put it here. I'm just giving you a few seconds to complete this. Anyway, we can modify the colors later. So what do we need to do now? We need to get the color information into the shader as well. And as the color information goes together with the geometric point, it's also an attribute. So everything which is connected to one corner point, to one vertex, is an attribute. So we just go to our Vertex shader here and we add an additional line. I'm just lazy, I'm duplicating this line and I tell them, hey, I've got another attribute which is a vector of 3 because we have RGB values. And I tell them this is my in color. So now we've got a new variable inside our Vertex shader. Take care to use the Vertex shader, not the Fragment shader. So we've got a new variable which could hold the colors and which could work with it. We need to populate this one later, but first of all, how do we get now the color which can only reach as an attribute into the Vertex shader into the Fragment shader? Well, there is another variable type for shaders, which makes it possible to send data from the Vertex shader down the pipeline to the Fragment shader. And the nice part is it will get interpolated along the way, because remember, we are having 3 corner points here. We just get the RGB values for every corner point. But for the triangle, we want this nice gradient to have the interpolation along the surface. And this is happening when we are using a so-called varying variable. Varying vector of 3 interpolated color. So what does this mean? I'm coming up with a variable which is also a vector of 3, so holding RGB values, and I give it the name interpolated color because this is what will happen with it. It will get interpolated along the triangle. So I'm just first of all declaring this variable, and of course I need to take care that this variable gets populated. So just another line inside the main function of our shader which says the interpolated color is populated by the original color, by the ones which is sent to the shader. This may look a bit strange now on the first strike because you may say, hey, nothing is happening there. You're just passing out the same color which came in. You're right, but OpenGL is now taking care of this variable, this interpolated color variable, and is really calculating the proper color value for every single pixel of our triangle. So we don't need to do much more than this. We need to have this variable called varying, and we need to populate it with a value initially inside the Vertex shader. So for the one corner point, this one will get populated red. For the other one, it will get populated green. For the next one, populated blue. And these 3 values are passed down the pipeline and will get interpolated. So we get a gradient on the triangle. But to be able to access this interpolated color, we need to have this variable not only in the Vertex shader, but just the same way in the Fragment shader as well. So we copy this entire line to make sure we don't misspell it. And we just go down a few lines. And above the main function, oh sorry, I did not copy correctly. Above the main function of the Fragment shader, we just do this variable declaration here as well. So we've got the varying vector of 3 interpolated color in the Vertex shader, just like we have it in the Fragment shader. And here's a big difference. In the Vertex shader, it is an output variable because we are populating it and sending data out. And in the Fragment shader, it will be our input variable. We are getting data into it. So we can use it in the Fragment shader to set the color, because now it automatically has a populated, interpolated color value for us. So let's come up with something like this, because it's a vector of 3 and GL frag color is a vector of 4 because it holds R, G, B and alpha. So we need to cast up the value again. So we tell them I want to make a vector of 4. The first 3 elements, which are RGB, should be taken from this interpolated color, and then just an alpha channel of 1 to make sure we are seeing this one. But the major point here is we've got the varying inside the Vertex shader and we've got it inside the Fragment shader, and they both need to be spelled exactly the same, so the shaders really can cooperate on this variable together. Otherwise we may get anyway a linker error later when we compile the program, because OpenGL will tell us, hey, you're trying to set a variable here, but I can't find it in one or the other shader. So just make sure you copy a line which is holding a varying always to the Vertex and the Fragment shader. So now inside the shaders our work should be done, because we are providing a new variable with color, we are providing a varying, we are populating the varying with the color that we get into the shader, and we make sure that the interpolated color of this varying is sent to the final output color of this one pixel which just gets processed. The only point left now is how do we get the color here again? Well, it's just the same like for the Vertex. And this is why I already came up with this variable here as color location, which can hold the location of this color variable inside the shader. So let's copy this one and let's go down to the function called GL create shaders, because this is the point where we initially got the location for this one here as well. So taking this one, oh no, I'm taking this one here not to misspell it, rolling down to the function GL create shaders. Once more, we compiled our shaders, we attached them to a program, we linked the program, and then we got the location of this variable in Vertex. And just for in color, it's the same. We only need to change our global variable to store the data in. So it's GL color location. So just one additional line working exactly the same. Please take the shader which is hiding, or the 2 shaders which are hiding behind this program ID. Look for a variable with this name and get the location of it, and store the location in my global variable. So we just have access to this variable inside the shader. That's the one step we need to do, and you see it's really exactly the same like we did it for the Vertex. And now that we know how to send data to this variable in the shader, we need to send the data. So going back to our render function now. And here we've got the line which is sending already the data for the Vertex location, and for the color it will be just the same. So again, duplicating this line is a good point to start. Telling him, hey, you're not sending to the location where the Vertex information is processed, but you're sending to my color location. And my color array is just made up the same way. We've got floats, always 3 values go together, RGB, and we don't need to get the data from the vertice array, but from our color array. But you see the lines are very similar. The functionality, of course, always is the same. We know where to send the data to into the shader. We know where to get the data from. And we know how the data is formatted. So we can explain OpenGL by this function GL vertex attribute pointer where to find the data, how to read it, where to send it to. And after we've done this, we can again call the draw array stuff. So this was just a quick way of implementing a new variable into the shaders, passing the information from the Vertex shader to the Fragment shader, while it gets interpolated, and then we use it in the Fragment shader. So let me just first of all compile this one and run it to see if I haven't brought in any mistakes, or I just realized what mistakes. Sorry. Because I told OpenGL, here is where you should send the data to, but I did not open the door to be able to send data there. So I'm just copying this line, enable Vertex attrib array once, and I need to tell him, hey, now I want to enable the location of this variable to be able to receive data as well. And as usual, everything that we open, we should close again. Oh. So, opening the door for this variable, telling him where to find his data, how to send it there, closing the door again, only after we've drawn, of course. This should work if I'm right. Let me check. Compiling this one, running this one, and the result on your side should be something like this as well. So now we really send the color to the shader as well. Red corner point, green corner point, blue corner point. And you see, just by use of this varying, we have this interpolation going on here on the surface. So I'll leave you just alone for a few seconds with this one here as well, so you can check you've got this setting properly as well. Okay, hopefully you all got this result by now. Then you really made one more major step to getting your shaders running and to understand how this is working, hopefully. Now we need to come up with one more thing. We've got the attributes, which are all the information related to one corner point. We've got the varyings, which allows us to send data from the Vertex shader to the Fragment shader and getting it interpolated along the way. And now we need one more thing. There's one more kind of variable type in the shader, which are the so-called uniforms, which means a variable which is holding the globally same value for all the shaders at the same time. So a uniform would always be something like light source inside your scene, or as well some matrices describing the world. In our case, we will now bring in a uniform with a simple float to be able to manipulate the scene based on this value of the float. Just to keep it simple, to give you the idea how this is working. So let's bring in this new variable. Again, just like the attributes and uniforms, we need to define this variable above the main functions in the shaders. So we come up with something here, which is called uniform, and which will just be a float, and we call it, how should we call it? Factor, which means this will hold some kind of value to change something. We could use this factor on the one hand to move the triangle, and on the other hand to change the color. So that's the nice point about uniforms. You can use them in the Vertex shader and in the Fragment shader just the same. So I'm copying it just to the Fragment shader as well, because this uniform will be available in both of the shaders. So we just brought in the uniform. Now let's think about what should we do with it. Let's say we will use this factor to move our triangle up and down. So I will come up with a new line here and tell it that the GL position, which is now already populated probably with the geometric information, I want to raise the y value. So I tell them GL position.y, which allows me to access only the y value, because this one is holding x, y, z, and w. By writing like this, I'm able just to access the y value, and I'm adding to it the factor, our uniform. Which means this simple line, based on this value of the factor, will take our triangle, move it up and down, whatever we put into this variable factor. That is our effect on the geometry. And as well, we will use the uniform to have effect on the color. So I just take this factor as well and use it as a multiplier for my color. Which means if this factor gets very small, our color will get darker. If I make it a big factor, our color will get much lighter till it's pure white. This is indeed usual way how you could bring in some brightness factor to your application. Of course, there are different ways to do it better, but that's just for us. For our example, it's pretty fine. So we just have one new variable in both shaders, which also has effect on both geometry and color. Still, I agree, quite useless, but it should just show you how you can do this. Okay, so we've got this new variable. Again, how do we get our data here? Well, just like we did it for Vertex and color, with the only difference, those were attributes because they were related to geometric corner points. The uniform is not related to any of the corner points because it should be the same for all of them. So we just will have a different function for this. But first of all, we need a global variable in our application to store the location of the variable factor inside the shader. So I just extend this declaration here where I already have a variable for the vertex and for the color, and I call it as factor location. Just to store the location of this variable inside the shader, so I'm later able to send data to it. Okay, let's copy this one. And let's go down again to the create shader function, because this is the point where we always grab all the locations of the variables for later use. Okay, this should be the place. And of course, now it's not the GL get attrib location, but it's the GL get uniform location. And I'm just checking the chat here, just a second. I don't want to miss anything. Okay, so it's not GL get attribute location, but it's GL get uniform location. But basically it works the same. It gets a program ID in which it should look for this variable that we are going to tell it now. And my variable is called factor. So again, look into this program, look for a uniform with this name, get the location of it and store it into my global variable inside my application. So I know how to send data to this uniform inside the shader. But you see the syntax going along with the attribute location is quite the same. Okay, now we've got the factor variable inside the shader. We have a handle to it because we have the location. Now we need to send data to it. So let's grab this one. I'll just give you a few seconds to check your code against this one here. Okay, let's send data to our uniform in the shader. Of course, again, this is happening in our render function. So here we got our render function. And for the attributes, we needed to enable to open the door to send data there. For uniforms, you don't need to do something like this. For uniforms, you just go ahead and tell OpenGL that GL uniform should get data. And you see now that the IDE is already providing me a bunch of functions. And this is because for a uniform, you need to tell OpenGL what type this uniform is. So I'm using now one float. So I will take uniform 1f, give him the location, and give him just the value. So let's make it 0.2, for example. Oh, that may not be enough, 0.5. Which means now it's sending my value 0.5 to this location in the shader, which means this factor will become 0.5, so the y value will raise by 0.5, and this factor as well, which means our color will get darker by 50% because I'm multiplying by 0.5 my color. So if I've done this wrong, our triangle should now be moved up quite a bit and should be way darker in the colors. Let's see if I haven't messed it up. Yep, and this is the effect we wanted to get. I hope you can see this. It's moved up because we have moved it up by 0.5. So we had an effect on the geometry and it's way darker than it was before. That's just because I changed the color. Now let's make it more visible. The best way to do it is to have a variable where the value is permanently increasing and we are sending it to the shader over and over again. So let's just bring in a variable holding a value for this uniform to show you that this is really called over and over again. So you really see that we're still in a render loop. Let me bring in one additional variable somewhere here. So let's call it GL float and just call it runner. Runner should be 0.0 in the beginning. And we will work with him. And now it's really just simple coding. I will take this variable and always send it to the uniform in our shader. And not to keep it all in one place, I know that's not clean coding. I will just tell the runner to increase by 0.01 and to make sure if the runner goes over a certain value greater than 1, it should be cut down again to -1. So it means our triangle should always move to the top, come back to the bottom, move up. And while it's moving up, it should change his color from brighter to darker if I'm right. But let me just check. Yes, this is what is happening. So it's moving up by just changing this one value. And as you can see, the color is changing because with a runner value or variable lower than 0, of course, the colors multiplied by 0 or a minus value always are black. So only at this point where it reaches a value greater than 0 and coming closer to 1, it gets back its full colors. This is what we really wanted to achieve here. Okay, so just to sum it up once more, because although this was just a 2-hour session till now, you really learned, get to know about the shaders, that they are just strings first of all, written in a certain language of course, OpenGL shading language, GLSL, but it's just a string in the end. We took those strings, we compiled them by OpenGL functions, we took the both compiled shaders and linked them into a so-called program object, and then we just grabbed the locations of variables inside the shader to be able to send data there. So these are indeed the steps that we have taken today and which are the basics of modern shader programming today. I guess these are really the basics. Whatever you will do in the future, you need to understand this technique. There are slightly different processes to this technique nowadays as well, mostly for desktop. We will catch up with those techniques later in a different workshop on shaders as well. But for today, I guess this should be it, because we came up really with the basic shader programming. And hopefully you all could follow me along this one, because with this program that you should have right now, you really have a minimum setup for shader programming, which is fine. And you should always keep these simple programs to look up stuff again, just to remind yourself how was this working. Anyway, we will do a sequel to this one, and to do more tricky shader stuff quite soon. But I guess we will call it a day for this one right now. And I will upload this one on YouTube as usual, so you can follow this one on YouTube as well. I will post all the necessary links as well on YouTube. Just an information for you as well. I'm trying to do in December just a sequel workshop to this one, where we will use the shader technique to program WebGL as well. So for those of you who are interested in how to do 3D programming in the browser, we will do this one in WebGL, in JavaScript. And you need this shader know-how as a basis. If you don't have this shader know-how, you won't be able to follow us, because WebGL only makes use of shaders. So without shaders, you won't be able to do this. Okay, that's it from my side. Thanks for watching today, and stay tuned on the website opengl2go.net for any upcoming workshops or for the podcast. You may check out the blog from time to time just to be sure you don't miss anything. And I hope you have learned something today. As usual, if there are any questions, reach out to me, contact me on Twitter or on the blog itself, or maybe even visit the page of my company deCode, just to get information about what we are doing. Thank you for watching this time, and hope to see you next time. Bye!